I'm a research scientist at the Sims University of Oklahoma and NOAA National Severe Storms Laboratory. And I work for NOAA's OneOnForecast research and development program. So I want to begin with thanking my co-author, Pat Skinner, for sharing his slides with me for this presentation, and also the entire OneOnForecast team at National Severe Storms Laboratory for this work. So the OneOnForecast system is a frequently cycled regional storm scale ensemble prediction system for a very short-term prediction of hazards. We can predict any kind of weather, but for the purpose of this talk, we are focusing on severe thunderstorm hazards. Now, we have been working on the OneOnForecast system real-time at the Hazardous Weather Testbed Spring Forecasting Experiment for several years since 2017. And part of the activities is to have an expert forecaster. We interrogate the guidance products every day and then give us feedback on what we can do to improve our products. Now, Dave Imey, who was a forecaster at the Storm Prediction Center for 30 years, he gave us feedback in 2017, and his #1 recommendation was outlined here. I'm going to read it loud. So he said, training, training, training. There needs to be examples illustrating the most effective ways to use WAFs. Also, all of the available product strengths, weaknesses, how to use them effectively, etc., need to be included. And effective training will go a long way to enhancing the effectiveness of OneOnForecast. So basically, his feedback emphasizes the importance of post-processing and effective use of those products for issuing watches and warnings. So to place the OneOnForecast system in NOAA's forecast continuum of environmental threats, or the facets framework, which is the next generation severe weather forecast and warning framework at NOAA, you can extend this out to subseasonal scale. So basically 3 to 4 weeks advance in time in the CPC precipitation outlook at subseasonal scales. Now, Storm Prediction Center starts issuing convective outlooks out about a week ahead and then continuously refine the area in space and time. And as you come closer to the event, you start getting regional storm threats, like when and where the storm will start or end, what storm types, how widespread, general movement, etc. And as the events is closer in time, watches and warnings are issued, and the storm scale ensembles like the OneOnForecast system can provide guidance between the watch and warnings, so which are basically individual storm threats with very high spatial and temporal specificity, like where this storm will track, what are the threats for this storm, like hail, extreme rainfall, or wind or tornado risks. And when I say numerical weather prediction guidance, that is really based on this article back in 1990 by Douglas Lilly. I have another quote here that really describes the real and practical challenge of OneOnForecast type systems. So basically to make it usable, which is the short time scales and expected rapid perishability of convective storm predictions compel almost instant transmission of output, preferably in some form which is visually acceptable to the forecasters. So basically, it is saying that we have a time problem. So if you think of the global models like the GFS, you can get a 340-hour forecast, and it takes about 6 hours to create the visualization products for that. And that is fine. But when you are issuing the next 3-hour forecast, and if it takes 2 hours to generate the visualization products, then you basically lose the value for most of the products. So because of these, the first thing we will have to do is to generate the guidance products very quickly. And the second problem is that we are disseminating these products. Mainly, our primary audience, main audience, is the operational meteorologists. So, if they are working on severe thunderstorm events, they are already in a considerable time pressure, and so we have two competing constraints here. So we have the time constraints. To basically produce the guidance products, we have to generate the products really quickly and make those very easily interpretable so that they do not take too much of forecasters' time. And that also means that we have the visualization challenges, special visualization challenges. We are interested to produce guidance products from individual thunderstorms, and thunderstorms are not going to cover over most of the domain. They are discrete, rare events over the domain, and some probabilistic products are more effective than others. Whether you're looking at a continuous variable like the 500 millibar height, or discrete variables like composite reflectivity or updraft helicity. So if you want to utilize the full complement of probabilistic guidance that an ensemble can provide, we have to be very careful about how we visualize those guidance to hopefully impart as much information as possible in the least amount of time. And basically, that is the motivation of what we are trying to do with this project with the OneOnForecast product guidance. So here I want to give a quick timeline of what does OneOnForecast guidance would look like when we run this in real time. So on the right here, you see time in minutes. So from the forecast initialization time, if you want to run the model immediately, we have to collect and process all the available observations of ongoing convections that are going on, and we are going to assimilate those observations into the model, and we assimilate those observations to create the model initial condition. And it takes about 10 minutes to for the ENCAPE data assimilation software that we use to assimilate all those observations into our Ensemble system. And then it takes about, so in total, it takes about 15 minutes to launch the forecast after the initialization time. And we have customized Python-based post-processing and visualization software that we use to generate the guidance products that are also run in parallel with the model. So so we can generate the full suite of visualization products in 30 minutes of the initialization time for a 3-hour forecast. So basically, what we have now is 2.5 hours of usable forecast data. So here's the website, NSSL website, where all the products are displayed when we run the system in real time. So we produce like more than 250 guidance products, and we generate approximately 20,000 images every 30 minutes. So, as you can tell, most of the users cannot interrogate these 20,000 images every 30 minutes. So every forecaster is different, and forecasters have to have the flexibility to look at the forecast products that are most useful to them on that day. So we cannot just get rid of these products because they might be useful on one day, even if they are not useful 9 out of 10 days. So basically, we are trying to package as much information as possible with these guidance products. And so I'm now going to go through some of the guidance products that we distill from the full ensemble information from the OneOnForecast ensemble, and talk about some of their strengths and weaknesses. I'm going to use this single forecast from a severe weather event on the 2nd May of 2018. That's as an example. So this is a forecast initialized at 20 UTC. So on the left is the composite reflectivity from a single ensemble member, and on the right you see the ensemble mean composite reflectivity. So, and as you can see, there are two areas of interest, ongoing severe MCS over Kansas and Western Oklahoma. And also there is a developing supercells along Texas-Oklahoma border. And if you look at the ensemble mean on the right, ensemble mean looks very similar to the single ensemble member. The reason perhaps is because we are assimilating radar observations of the storm very rapidly and very often. And so we are able to accurately analyze the individual storms in the model. But also you do not have a lot of spread among the ensemble members for the storm location in the analysis. Now I'm going to loop this for the next 3 hours forward in time. So all of the forecasts are slightly different in terms of storm position, and we basically average those together, and that smooths the composite reflectivity field. So this is the problem of using ensemble mean for discrete forecasts. So it basically makes it look like the storms are dying, and in reality they are not. The individual members, as you can see, they are actually intensifying with time, and because there are special variations in locations, the ensemble mean looks like they are stratiform rain band, basically. So it is it provides misleading information in this context. On, so another way around that is to use the probability matched mean. So the probability matched mean will take the amplitude from the individual ensemble members and it will apply it to the ensemble mean field. So this is a very common technique, especially for QPF forecast, and it does help a little bit. So if we loop this forward in time, in this case, for a composite reflectivity field, you get a high amplitude reflecting the individual member, but however, the actual shape and the evolution of the thunderstorm doesn't match what forecasters would expect the storm to do for this case. So basically, an unphysical representation. And the reason being, by simply substituting high amplitude values in the probability matched mean from an ensemble member, it creates a physically unrepresentative product, as in this case. So basically it is useful, but it is providing deterministic information, but it can be misrepresent the actual storm evolution and the actual forecast. So the final sort of the pseudo-deterministic measure I want to show is the paintball plot. Each color here represents on the right, it represents a different ensemble member, and in this case, it provides also it is providing limited information from the each ensemble member in the ensemble switch. So if we kick this off, you see the special coverage potential from all the different ensemble members, and you can also infer some measure of probability from looking at how many individual ensemble members are stacked on top of each other. So in this case, we start to get some probabilistic information instead of just a pseudo-deterministic measure. Now, for full probabilistic guidance, this is really there is really two different ways to do that. If you think about each grid point within the domain, you have a distribution of potential values provided by the ensemble, and you can slice that. You can slice that based on probability density function, where you have a set of fixed thresholds, say the observed felicity, which is the proxy for mesocyclone greater than 60 meters square per second square. And then if you look at how many members are exceeding that at each different grid point, and you create a SWAT, basically a probability of mesocyclone occurring during this period, as shown here. So, and I just wanted to highlight these three different areas here. So on the top, you have high probability of rotation. And then as you go down, you have a low probability of rotation in central Oklahoma. So this kind of product, this provides an excellent measure of the likelihood of mesocyclone occurring, but it provides very limited information regarding the potential severity or the intensity of the mesocyclone. Now, the other way you can slice it, you can think of this as a CDF of the distribution. And if you pick a fixed probability value, say 10%, you must have at least 10% probability of an event occurring. And you see what value does it occur at. And then you can provide a measure of severity alongside the measure of the likelihood. So this is the 90th percentile of the 2 to 5 kilometer observed velocity. So, and when you look at this in tandem, you have this very high probability of only moderate potential severity in Kansas. So that makes sense. It is a mesoscale convective system, so it has it is less severe than a supercell. But if you have a tornadic supercell here, in central Oklahoma, and you have high probability of rotation and high potential of severity, and then low probability area where you notice actually very high value of observed helicity, and you have low probability and high severity. So it is really important to look at measure of both the likelihood and the severity when you are interpreting a probability guidance, and it provides a more complete view of what the ensemble system or the ensemble prediction system is providing here. So for the remainder of the presentation, I'm going to show a couple of examples of how different factors and ensemble design can influence what guidance might look like. So this is the first. So the first is an ensemble size. So you are looking at the paintball plots again. We have a 36-member ensemble on the left. So the versus a 18-member, which is what we are running in real time for the OneOnForecast, and then a 9-member forecast. So you can actually give the impression of differences in thunderstorm coverage and probability based on how many paintballs are stacked on top of each other. And similarly, perhaps dramatically, if you look at the ensemble max value for which is very popular for next day convective allowing ensembles, in this case, you include outliers from the individual members in the visualization. And as you can see, the purple values of the observed felicity, these are really extreme values, and this is associated with high and intense supercells. And if you have a really a large ensemble, it does a better job, but so it is a positive aspect of the coverage of the potential area of the intense supercell. But if you look, on your left, it looks like the world is going to end in central Oklahoma. So you have an entire tornado outbreak there with a 36-member, and with the 18-member, it's a little bit better. And then with the 9-member, it provides a more accurate reflection of where the intense supercell is formed and tracked in this limited spatial domain. And then, another important area is the neighborhood size. This is a vast topic, and you can give an entire talk on the neighborhood size. But in short, we have this 3-kilometer grid spacing, and generally, if you look at on the left plot, if you don't use the neighborhood, you have limited scale at 3-kilometer grid spacing for thunderstorm prediction. So you want to spread that information out. So, and the most popular way to do this is neighborhooding. And this is a post-processing technique, and neighborhood size dramatically influences what the actual visualization would look like, as you can see. This is, we typically use for OneOnForecast 4.5 kilometer neighborhood radius. So it spreads the grid scale information of primary storm track and intensities, but however, there is this is a very tiny neighborhood compared to most convection allowing ensembles. So what you see on the right is a 13.5 kilometer neighborhood, and as you can see, we lost all of the individual storm tracks in the guidance products with 13.5 product, and so that we are, but we are really interested in maintaining the the individual storm tracks. So this is another consideration when we are generating our visualization product. So in summary, the storm scale ensembles can provide skillful probabilistic guidance of individual thunderstorms, but the short duration and temporal resolution of the guidance creates a challenge for post-processing, visualization, and verification. And we have to be cognizant of how the guidance products are generated and what information it is intended to provide. I mean, familiar products like the statistical or probability math mean may not be appropriate for predicting rare discrete events like thunderstorms. So we have to effectively utilize the full suite of ensemble information to generate products that provide information on likelihood and also the severity of the event, and other considerations like ensemble size and post-processing techniques for neighborhooding and others do influence what the guidance products are that influence the guidance products that we look at. So this is my last slide, and I'll be happy to answer any questions.
Okay, we have time for maybe